Students, today as the third part of Ionic Equilibria, let us look at the definition of buffers, the mechanism of buffer action, then buffer index, and also the problems on the determination of pH of a buffer. Now, what are buffers? Now, just for curiosity, you take sodium chloride solution whose pH is 7. Now to this sodium chloride solution, which is also known as common salt solution, if 1 ml of 1 molar HCl solution is added to 10 ml sodium chloride solution, pH of NaCl solution decreases to about 1. Now look at this, from pH 7, the solution pH decreases to 1 unit, decreases to pH of 1 when we add just 1 ml of 1 molar HCl solution. Now look at another example. Now if we take equimolar concentrations of acetic acid and sodium acetate mixture, which has a pH of 4.75, and to this solution if you add same amount of HCl, that is 1 ml of 1 molar HCl to 10 ml of this buffer solution, then the pH of this solution decreases to 4.66, or its pH is almost unchanged. Hence, we can conclude that NaCl solution is not a buffer, but mixture of acetic acid and sodium acetate solution is a buffer. Then what is the definition of a buffer? A buffer is a solution which resists or opposes the change in its pH value or hydrogen ion concentration when a small quantity of an acid or a base is added to it. Chemically, buffer is a mixture of either a weak acid and its conjugate base, or a weak base and its conjugate acid, or a solution of salt of weak acid and weak base. The first one is called acidic buffer. So that is, acidic buffers are the buffer solutions which are prepared by mixing a weak acid and its conjugate base. In other words, mixture of weak acid and a salt of that weak acid with a strong base. Example, acetic acid and sodium acetate mixture, or carbonic acid plus sodium bicarbonate mixture, benzoic acid plus sodium benzoate mixture, etc. Now for examples for basic buffers are ammonium hydroxide plus ammonium chloride mixture. Friends, we have discussed what is a buffer solution. A buffer solution is one which does not allow change in its pH value when we add a small quantity of an acid or a base into it. Now the capacity of a buffer to oppose the change in pH value and maintain its original pH constant is known as buffer capacity. That is the capacity of the buffer. Now next is, what is buffer index? Buffer index is a measure of the buffer capacity. Buffer index is a quantitative measure of the buffer capacity. It is defined as, in terms of equation, beta is equal to dB divided by d of pH, where d of pH is the small increment in pH value that is caused due to the addition of small amount of strong base dB. dpH is the small change in pH caused by the addition of a small amount of a strong base Db. Now we will have questions on this. Define buffer capacity and what is buffer index. You focus on this. Next is buffer mechanism. Now the method or the way by which a buffer solution opposes the change in pH value, or more precisely change in H plus concentration by internal adjustment, is known as buffer mechanism. Now explain buffer mechanism will be the question for 3 to 4 marks. Now let us discuss how a buffer solution internally undergo adjustment in such a way that there is no change in H plus concentration or pH does not alter when we add a strong acid or a base into it. First case, let us discuss the mechanism of buffer action of an acidic buffer. Now for this, let us take acetic acid and sodium acetate mixture. Now in the solution that is prepared by mixing acetic acid and sodium acetate, note that acetic acid is a weak acid and sodium acetate is a salt which is called strong electrolyte. So hence acetic acid ionizes partially. Only a few molecules of acetic acid will ionize into acetate ions and H plus ions as per this equation. Sodium acetate ionizes completely as CH3COO Na, giving rise to CH3COO minus. So minus is there as charge plus Na plus. Thus, there are more number of acetate ions because they are furnished or supplied by both the electrolytes, and some Na plus ions, few H plus ions, and some unionized molecules of acetic acid. Now suppose into this solution a small amount of an acid is added. So what an acid is going to do is the acid is going to increase the H plus ions in the solution. Now the H plus ions of the added acid are neutralized by acetate ions present already in the solution. According to this equation, H plus of the added acid will combine with acetate ions of the buffer to form acetic acid. In other words, acetate ions will consume the H plus ions produced by the added acid and thereby does not allow change in H plus concentration, or pH of the solution remains constant. So by this reaction, H plus of the added acid will react with acetate ions which are present in more number in the buffer solution to form acetic acid. Similarly, if a small quantity of a base is added, now we all know that base is a substance which produces OH minus ions. The OH minus ions of the added base, if they are not neutralized, the H plus concentration will go down, because when OH minus increases, H plus should decrease, since the product of these two ions should remain constant, which is called ionic product of water. Now if H plus concentration decreases, pH value increases. But in this buffer solution, that will not happen. Now how that OH minus concentration increase is cancelled. Now the OH minus ions of the added base are neutralized by H plus ions which are already there in the buffer solution and form water. Now the reaction is OH minus of the added base plus H plus of the buffer solution to form water. Now again you may ask the question, now if H plus ions of the buffer solution are consumed, H plus concentration goes down, therefore pH will increase. Again, due to the formation of water, the degree of dissociation of acetic acid increases. That is, the molecules of acetic acid which are there in the undissociated form, some of them will ionize in such a way that the original H plus concentration is maintained. In other words, pH of the solution does not change. When an acid is added or a base is added, H plus concentration remains constant or pH of the solution remain unaltered, because the buffer solution undergoes adjustment in such a way that whatever the effect is caused, that cause is cancelled. So if acid is added, H plus ions of the added acid are neutralized by uh, acetate ions which are there in the solution. When base is added, the OH minus ions of the base are cancelled by or neutralized by H plus ions which are there in the buffer to form water. So like this, the buffer undergoes internal adjustment and maintains the constant pH value, or H plus remains constant as it's before the addition of acid or base. Hence, acetic acid and sodium acetate mixture acts as a buffer. This is how the solution maintains its constant pH, and thus it acts as a buffer solution. Similarly, let us see how a mixture of ammonium hydroxide or ammonium chloride will act as a buffer. Now, this ammonium hydroxide and ammonium chloride mixture is called alkaline buffer because the base is used here to prepare the buffer solution. Again, in this example also, or in any buffer solution, one component or one compound will be in a weak acid or a weak base. The other one is a salt of that weak acid or weak base. So here also, students, ammonium hydroxide is a weak base and its salt is ammonium chloride. We have used one term known as conjugate acid and conjugate base. If ammonium hydroxide is a weak base, when it undergoes ionization, it forms NH4 plus OH minus. NH4 plus is called conjugate acid of ammonium hydroxide. Now, to explain the mechanism, again, ammonium hydroxide is a weak base which ionizes partially, like NH4OH forming NH4 plus ions and OH minus ions. Since partial ionization takes place in the solution, there are few ammonium ions and few OH minus ions. This OH minus is to be concentrated here. In other words, you have to look into the concentration of OH minus to discuss. The OH minus concentration should not be altered by under any circumstances. Then only this solution is going to act as buffer. Now the salt ammonium chloride ionizes completely as NH4Cl giving rise to NH4 plus and Cl minus, and since ammonium ions are produced by both the electrolytes, the concentration of ammonium ions is more in the solution. OH minus is fixed. There are some molecules of ammonium hydroxide which are not ionized, and some Cl minus ions also. Now, as I mentioned, OH minus concentration is very important. That should not be altered, because if OH minus changes, H plus also changes. So our discussion is how this mixture is not going to allow the change in H plus or OH minus. In either way we can do it. As per the any product of water, in any solution there will be both H plus as well as OH minus ions. If one changes, the other one also changes. That should not happen in a solution to act as a buffer. Let us discuss how this happens. So it is only an internal arrangement of the reaction or the system itself. Now suppose if we to this solution, if we add a small quantity of acid, so acid is one which supplies H plus. If it is an ordinary solution, on adding HCl, there is an increase in H plus concentration, or there is decrease in pH. But to a solution of ammonium hydroxide and ammonium chloride mixture, when we add, if we add a small quantity of acid, the H plus ions of the added acid are immediately neutralized by OH minus ions which are already there in the buffer solution. So in other words, we can say as soon as the acid is added, the OH minus ions will go and attack H plus ions, or they react with H plus ions to form water. So therefore, what is the net change? H plus concentration is not going to increase, but OH minus decreases. The OH minus concentration goes below the original value. To maintain the original concentration of OH minus, since there is formation of water, concentration of the solution decreases or dilution of the solution increases. We all know that the degree of dissociation of a weak electrolyte, here ammonium hydroxide, increases due to increase in dilution. So therefore, in order to maintain original OH minus concentration, some molecules of ammonium hydroxide ionize. Therefore, OH minus remains same as before addition of acid. In other words, OH minus concentration remains constant, or pOH is unchanged, or pH is unaltered, because pH plus pOH is always 14. Similarly, if one question may arise here, dear students, when we add acid from the external agency, or if we add an acid from the external source, the H plus ions are neutralized by OH minus ions. Now the question may be, the doubt may be, why not Cl minus? Because Cl minus is carrying opposite charge to that of H plus. So they should quickly attract together to form HCl. So you may be right, but when HCl is formed, HCl is a strong electrolyte as we know. It ionizes back, forming H plus and Cl minus. So therefore, net reaction, effective reaction is H plus of added acid are neutralized by OH minus present in the buffer. Now similarly, instead of adding an acid, if we add a small quantity of base, which is going to increase OH minus, the OH minus ions of the added base are immediately neutralized by ammonium ions, oppositely charged. So OH minus ions are cancelled by oppositely charged ions. Which are the oppositely charged ions present in the solution? NH4 plus ammonium ions. There are more number of ammonium ions. They will come and neutralize these OH minus, and therefore there is no change in OH minus, or there is no change in H plus, or pH is constant, or pH of the solution is not altered when we add an acid or a base into this buffer also. Now students, when we add an acid, generally the acid is going to increase H plus concentration. In the buffer solution, the oppositely charged ion should cancel. So negatively charged ion. When we add a base, it is going to increase OH minus concentration. OH minus should be cancelled by oppositely, that is positive ions. So in case of ammonium hydroxide and ammonium chloride mixture, OH minus ions are cancelled by ammonium ions. In case of an acidic buffer, OH minus is cancelled by H plus. So like this, we can easily explain how this solution, that is buffer solution, opposes any change in pH value when we add an acid or a base into that solution. Now buffer solutions are very important in industry, research, and even in maintaining the normal health of the living organisms. Now buffer is a mixture of weak acid or weak base with its salt. So therefore pH of a buffer solution, because most of the reactions occur at a particular pH value. Any change in pH alters the rate of reaction, or it may, deviation from that pH may cause diseases in living organisms. So the pH of a buffer solution depends upon the dissociation constant of weak acid or weak base used, and also relative concentration of the salt used, and also acid or base used to prepare the buffer solution. The relationship between the relative concentrations of the salt and acid or base used to prepare the solution and its dissociation constant of weak acid or weak base is given by an equation known as Henderson-Hasselbalch equation or simply Henderson equation. For an acidic buffer, the Henderson equation is pH is equal to pKa plus log of concentration of the salt divided by concentration of acid. Now pKa is negative logarithm of Ka, where Ka is known as acid dissociation constant of the weak acid. Similarly, for an alkaline buffer, that is, if we prepare a buffer solution using a mixture of weak base and its salt, then Henderson equation is POH is equal to PKB plus log of concentration of salt divided by concentration of base. Look at the changes here. POH is negative logarithm of hydroxyl ion concentration. pKb is negative logarithm of base dissociation constant. This equation helps in calculating the pH of buffer solutions prepared by mixing known concentrations of weak acid or weak base with its salt. Alternately, it also helps to calculate molar amounts of the acid or base and the salt, that is these two compounds, to be mixed to get a buffer of required pH. It is necessary to have buffers of a definite pH for industrial purposes as well as in research. Biological fluids like blood, saliva, gastric juice, pancreatic juice, etc. need the maintenance of a specific range of pH for their normal function. Deviation from this specific pH range causes diseases or abnormalities. Therefore, even in biological systems or in industries or in research, buffers play an important role to get the desired production yield as well as the normal health in case of living organisms. Now, if in the examination there will be a question like this: explain the buffer mechanism of either acidic buffer or basic buffer, and there may be problems on this Henderson equation, and there will be derivation of Henderson equation. Let us see how to derive this Henderson's equation or Henderson-Hasselbalch equation, which is applicable for determining the pH of buffer solutions. Students, don't be confused. There are two formulas. One is pH, an ordinary solution. pH of an ordinary solution is equal to minus log of H plus concentration. But for buffer solutions which are prepared by mixing two different compounds, one is weak acid and its salt or weak base and its salt, pH is given by pH is equal to pKa plus log of salt concentration by acid concentration. So this difference should be noted. Now consider Henderson equation derivation for an acidic buffer. Consider an acidic buffer like acetic acid and sodium acetate. Now here, as we know, acetic acid is a weak electrolyte which ionizes partially as CH3COO minus, that is acetate ion, and H plus ions. Whereas sodium acetate is a salt which ionizes completely, forming acetate ions and Na plus ions. Note that we have mixed these two compounds and both the compounds are present in the same container. Now for the dissociation of acetic acid, if you apply the law of chemical equilibrium, equilibrium constant is equal to concentration of products divided by concentration of reactants. Using this general formula, we can write Ka is equal to, why there is Ka? Ka is there because of the compound used here is weak acid, therefore its equilibrium is acid dissociation constant, which is equal to concentration of acetate ions and concentration of H plus ions divided by concentration of acetic acid. Note that all the species are written within the square bracket which represent concentration. So in the numerator we have products which are CH3COO minus acetate ions and H plus ions. In the denominator we have the molecules of acetic acid which are not ionized. So taking H plus into this side, H plus is equal to just a rearrangement. We get this expression, and take negative logarithm on both sides. Minus log of H plus is equal to minus log of acetic acid by acetate ion concentration plus minus log of Ka, or pH is equal to, because minus log of H plus is nothing but pH is equal to log of acetate ion concentration by acetic acid concentration, that is constant number of molecules or moles of acetic acid which are remaining unionized at equilibrium level, plus pKa, because minus log of Ka is pKa. Similar to minus log of H plus is pH, minus log of K is pKa. Since most of the acetate ions are derived from sodium acetate salt, because here sodium acetate is a strong electrolyte, acetic acid produces few acetate ions. Number of acetate ions released by acetic acid molecules is negligible compared to the number of acetate ions produced by the salt sodium acetate. So therefore, concentration of acetate is taken as equal to concentration of the salt mix. So therefore, pH equals pKa plus log of concentration of the salt divided by concentration of the acid. So this is Henderson equation for an acidic buffer. So this derivation may be there in the examination for 4 marks. So therefore, here while deriving, first you have to take the acetic acid dissociation concept and apply the law of equilibrium, that is dissociation constant of acetic acid is equal to concentration of products by reactants, and take negative logarithm and derive that. We know the pH formula, pKa formula, and from that we can easily derive this Henderson equation also, which is more useful, as I said in the previous part of this discussion. And once derivation of Henderson equation for an acidic buffer is derived, they may ask derive Henderson equation for an alkaline buffer. Then how you are going to derive this? For an alkaline buffer means one compound should be a weak base, the other is its salt. Now for this, let us consider ammonium hydroxide and ammonium chloride mixture for this type of buffer. When these two compounds are mixed to get the solution, which is called buffer solution, the weak base ammonium hydroxide ionizes partially, as we know, students. Ammonium hydroxide ionizes partially to form ammonium ions and hydroxyl ions, OH minus plus NH4 plus. Whereas the salt ammonium chloride ionizes completely because it is a strong electrolyte. All salts are strong electrolytes. Almost all of the molecules which are added will ionize completely. So there is a irreversible sign here. You have to note this. If there is a double-headed arrow, it is a reversible process. If there is a single-headed arrow, it is an irreversible process. All these points are to be noted, dear students. So it forms ammonium ions and chloride ions. Now to proceed, we have to take the reversible process dissociation of ammonium hydroxide. So for that, because we are going to apply the law of equilibrium, ammonium hydroxide ionizes into NH4 plus OH minus. Reversible sign is here. Apply the law of chemical equilibrium. K equilibrium is equal to, or here it is Kb by Kb, because here it is base. The base dissociation constant is used here. Kb is equal to, again, concentration of products. Here the concentration of products are ammonium ions into concentration of OH minus. Here you have to, you should not write plus here. It is a product of concentration of the two ions divided by concentration of ammonium hydroxide molecules which are remaining unionized at the equilibrium stage. So rearranging it, OH minus, and all these things you can observe here. Procedure is same as we had derived for acidic buffer, taking negative log on both sides. Minus log of OH minus is equal to minus log of ammonium hydroxide by ammonium ions. Here it is NH4 plus in square bracket, plus is there, plus minus log of Kb. Since minus log of OH minus is POH, minus log of Kb is PKb. and most of the ammonium ions are derived from ammonium chloride salt. Therefore, concentration of ammonium ions is taken as equal to concentration of ammonium chloride salt. So therefore, in place of ammonium ions, we can write concentration of the salt ammonium chloride. So hence, pOH is equal to pKb plus log of salt concentration by base concentration. This is Henderson's equation, which is applicable for basic buffer or alkaline buffer. Now for alkaline buffer, since weak base is used, the formula becomes pOH is equal to pKb plus log of concentration of salt divided by concentration of the base. Since pH plus pOH of any solution is equal to 14, if pOH is known, pH of the buffer solution can be calculated. Deriving the Henderson equation, let us see its use. Henderson's equation is used in calculating the pH of buffer solution when the concentrations of the acid or the weak base that is used and the concentration of the salt are given. Now here we have an example for that. Calculate the pH of a buffer solution prepared by mixing 0.2 mole of acetic acid and 0.25 mole of potassium acetate per liter of the solution. Given dissociation constant of acetic acid is 1.8 into 10 to the power of minus 5 at 25 degrees Celsius. Students, while solving the problems, you have to look into the data that is given and what is being asked. So you have to focus on that. Now here data given is acid dissociation constant is given, that is 1.8 into 10 to the power of minus 5. Concentration of the acid, that is acetic acid, is given here, that is 0.2 moles per liter, and concentration of the salt, that is potassium acetate, is 0.25 moles per liter. Now what is the formula to be used for the determination of pH of buffer? Note that pH is equal to pKa plus log of salt concentration by acid concentration, because here the buffer solution is prepared by mixing acetic acid and potassium acetate. Therefore pH formula is pH is equal to pKa plus log of salt concentration by acid concentration. Now pKa is equal to minus log of Ka plus log of salt by acid concentration. Substitute the value of Ka, that is 1.8 into 10 to the power of minus 5, plus log of salt concentration is 0.25 and acid concentration is 0.20. Now simplify all these. On simplification, you get the pH of the buffer solution is equal to 4.842. Now in the examination, they may ask to calculate the pH of a solution. Now pH of an ordinary solution, dear students, is given by negative log of H plus concentration. Now therefore, you look at the problem, what is given there, calculate the pH of buffer solution. For buffers, pH formula is different from the pH of an ordinary solution. So therefore, you read the problem once or twice and then use the formula, write the formula for which you will get marks. In the scheme of evaluation, there will be marks for formula, marks for substitution, and also for answer. Separate marks will be given. Therefore, don't forget to write the formula. Dear students, with this we come to the end of this session, and similarly they ask to calculate the pH of a buffer solution prepared by mixing, say, some concentration of ammonium hydroxide and some concentration of ammonium chloride, and when that is the problem, then the formula to be used is pOH is equal to pKb plus log of salt concentration by base concentration. So similarly you can solve that. There will be 4 marks for this problem, and therefore under buffers, so we have these probable questions: define buffer, what is buffer index, then derivation of Henderson's equation, mechanism of buffer action, and problems on Henderson equation. You can focus on these points, study well, and in the examination read the question paper twice, and what you know you answer it first, then for the remaining questions you can try. So dear students, with this we come to the end of this session. I wish you all the very best in the coming examination. And for any queries, you call me. My phone number is 901999508, or I have given the mail ID also. You can put the queries to this mail. Read well and do well in the examination. So that is all. Thank you one and all.